As we mentioned, solving the total cost under different n values and various t1 values are relatively complicated. So to help us solve the problem, we need to bring some help from coding. You can use Excel, MATLAB, or use this Colab as we introduced to develop algorithm to solve the shooting method or other methods. The first step to use our code is to establish a discretized time-varying demand. So for example, if we consider a discretization resolution, we call each of the discretized time step delta t. So the continuous time dimension will be discretized into 0, 1, 2, and then 2t. So the tmax now will be somewhat related to t times delta t. So here in our algorithm, we use delta t to set the resolution. You can definitely increase the number of delta t to make a better solution, but it typically requires more computational time. So with delta t, we can just arrange for our time dimension. In our problem, we start from time 0 and end at time 3. And then we use a range function to generate the discretized time axis from 0 to 3 with a time step 0.01. After we discretize the time axis, we can create our demand function. The first step, we need to provide this piecewise expression for the demand rate. So we have 3 pieces. Right? The first piece, the gradient is 100, 80, and 50. So to achieve this, we provide 3 pieces for demand rate, which is given by this figure. We use the small tricks of Boolean algebra. As we discretize the time axis into 0.01, so when t is smaller than 1, that indicates our index is around 100. So we can use 100 times the Boolean algebra that our index is smaller than 100 to activate the expression for the first piece. And then for the second piece, it indicates t is greater than 1 and smaller than 2. Based on this discretization resolution, the index should be between 100 to 200. And then we multiply it by 80, which gave us the second piece. So similarly, we can have the third piece when t is greater than 2. After we provide the demand rate, we can calculate its cumulative demand function. This is pretty simple in Python. Remember that we have a time step, delta t, in time axis. So when we calculate the cumulative demand, we need to take the integration. That means we need to times the detail here, which is delta t to some extent. So in this case, after we time it by delta t, we can calculate the cumulative sum of the demand rate to generate the cumulative demand curve. And then this figure shows our plot, which is exactly the same as what we expect. You can see here, first turning point is around 100. And then the second turning point is around 180. And the Tmax here, the demand is 230. And then we check the value of Tmax. In Python, the last value of the array can be visited by index -1. So we can print it out, verify that the last demand value is 230. So with the help of this Colab, we can first verify some calculation for case 1. Remember our case 1, we have our rent cost is much larger than the inventory waiting cost. So we have equal loads every time. The load is determined by the Tmax over number of shipments. So similarly, we just bring the initialization of our demand. The resolution is still 0.01. And then the range is from 0 to 3. Now we can plug in our parameters from the previous example. Note that here we only need rent cost because we assume rent cost is much larger than the inventory waiting cost. So to apply our formula, we can easily calculate this optimum n value using Python. Remember that this value actually is a float number, which is not an integer. Finally, get the integer number of shipments, we need to calculate the rounding function over number of shipments. For example, we can use the floor function, we can use the ceiling function. Both values can be used, depending on which one generates the lowest cost. Here, for example, we just choose the floor function. We take the integer which is small or equal to n. And then, based on this integer number of shipments, we can calculate total cost based on our formula. we have printed the original float number of n optimum value and an average headway, and finally our total cost. Here, let's verify our calculation. We can further plot cumulative arrival curve to double check. So here the blue lines are our demand function, and then our red lines are our cumulative arrival. This can be achieved relatively easy because we know every time our load is based on det max divided by the number of shipments. We just need to enumerate all possible time index from small to large. When the cumulative demand reaches the load, as time goes, we calculate the cumulative demand within this time range. So if the demand is smaller than the load, we accumulate the demand. Once it's reached the load V, we will dispatch this vehicle, and then the cumulative load is clear 0. Keep doing this, we can generate this exact plot for the cumulative arrival. So the most difficult one, or the reason why we need to use the coding, is to solve the routing method. So here, we still generate our demand as what we expect. The only difference is we further consider a finer resolution to provide a more accurate result. So remember, after we change the time step, we also need to change the split point for the curve. 1000 the index means 1 for the time. So here, we just apply our shooting method. Remember our logic. This is T0, this is T1. First, we need to check if T1 is outside the boundary of T max. When T1 is larger than T max, there will be an error. And then to generate the next shipment time, we consider this value, which is dt1, is given by this line. And then the gradient at T1 is approximately calculated based on the difference. So here you can see we ignore the time unit because later on, when we calculate the projected time point, if we also consider the index, there is no need to worry about the time step, as the time step will be cancelled. So here, without loss of generality, we'll assume the time step is 1. That's why we can just use the difference of the cumulative demand value to obtain the gradient. And then we draw a parallel line and then calculate this intercept. So this gives us the value of dt2. So to achieve this, we calculate dt2 based on the length of the bottom, which actually is t1 minus t0, and then times the gradient, which is given by the calculation. And then finally, we get the height of the triangle plus the initial location of this triangle. We can predict dt2. So after this calculation, we need to check if dt2 is beyond dt max. Otherwise, t2 is also beyond t max. If both t2 and dt2 are within a reasonable domain, we will return the index of t2. So this is our output. So here, let's see an example about how we use our algorithm to generate from initial t1 value. So here, we assume the t1 value is 1.26, so it's around index 1260. We put this value as our initial try, and then definitely the first shipment, the load of the shipment, will cover the total demand until t1. And then we use our function to generate the next shipment time, which is t2. So after we obtain t2, based on our shooting method, we can calculate the shipment. The load of this shipment is determined by dt2 minus dt1, which is this line. And finally, we can calculate the cumulative arrival to generate the cumulative arrival curve. Then here, as we plot, the blue one are the demand line, and then the red one are the cumulative arrival line. So here, let's see if we utilize this shooting algorithm, how should we solve the problem we just manually solved. So similarly, we're starting from t1 equals to 0.7. Actually, their index is around 700. And then assume we have at most 4 shipments. And then we apply our shooting algorithm as we just introduced for each shipment. And then we use a recursive method, when we get T2 from T0 and T1, we will replace the new T1 as T0 and T2 as T1, and then apply our method again to get our next T2, which is the next shipment time, the T3. So by doing this iteratively, we can generate as many as possible shipments. So we have a termination criteria. So if your projection from T1 to T2 is outside the visible range of Tmax, we will enforce that T2 equals to Tmax. Or in another case, we have reached the number of shipments, the most max shipments. For example, this is our last Tn, and then it's still not reached Tmax yet. So in this case, we need to enforce Tn equals to Tmax, and then guarantee that the rest of demand is all covered. To apply this algorithm to the problem, and we can verify our solution from the information we print out. The first shipment time is 0.7. The second shipment time is 1.5, as what we calculated. The third shipment time is 2.48, which is very close. And then the final cost, holding cost, is slightly smaller than what we calculated. So the small error actually is less than 0.2. It's because of the numerical resolution error. It's because of the discretization error. If we want to get more accurate results, we need to further use a higher resolution. And then last, we can implement the solution for total cost. Remember, our total cost has two parameters, n and t1. So here, for example, we set n equals to 4. Then our task is to enumerate all possible t1. To get the minimum holding cost, here we initialize holding cost to be all 0. And then we enumerate all possible t1 from 0 to 3. And then within this algorithm, that's our shooting method. And after this shooting method, given the number of maximum shipments, we can calculate this holding cost. And then we plot out this holding cost with respect to the selection of T1. And then we can get this curve. So this is the value of T1. And then this is our holding cost. And you can see that we do have a minimum point. So we print out the value, the optimum T1 value should be around 0.66. And then the corresponding cost associated with this T1 is 81.98, slightly smaller than what we get. Later on, you can switch the value of n . You can see when n equals to 3, the minimum holding cost is 100.8, which is larger. Let's say when n equals to 5, it's even smaller. So you can see the holding cost will always decrease as the number of shipment increases. That makes sense. The trade-off of the total cost lies in the increase of the fixed cost.